Welcome to The Explainer. Today, we're going to break down a fundamental rule of AI that really challenges almost everything we think we know about building smarter algorithms. And honestly, this concept has never been more relevant than it is right now. You know, for decades, there's been this kind of holy grail in computer science, the hunt for a single master algorithm. The big idea was to find one learning model that's just universally better than all the others at making predictions, no matter what problem you throw at it. And this wasn't just some pipe dream. This very idea, captured right here in quotes from some really foundational papers, suggested that some algorithms are just inherently superior, that we could prove they work well without even knowing the specifics of the problem, or what the paper calls the target function, which is just the true pattern we're trying to figure out. But what if this whole search, this entire quest for a universally best model, is actually based on a huge misunderstanding of how we even measure performance in the first place? Okay, let's really dive into this. So before we can even start comparing different algorithms, we have to agree on the rules of the game. And that starts with a really critical question. What does real performance actually mean? Well, this paper argues it all boils down to one key idea. And that idea is called off-training set error, or just OTS error for short. It's a simple concept, but it's incredibly powerful. It says the only true measure of an algorithm's performance is how well it does on data it has never, ever been trained on before. This is the real test of its ability to generalize. Okay, think about the difference this way. Judging an algorithm on data it's already seen, that's not a real test. That's just checking if it can memorize stuff. It's like studying for a test when you already have the answer key. But OTS error? That's the real exam. It tests the ability to predict, which, let's be honest, is the entire goal of machine learning. So this brings us to a crucial rule. Whenever we say one algorithm is better than another, we can only be talking about its performance on data it has never, ever seen. It's off-training set error. Now, with this rule set in stone, the paper's author, David Wolpert, drops an absolute bombshell. And this is where we get to the heart of it all, the no free lunch theorem. Using OTS error as the only fair way to measure things, Wolpert comes to a conclusion that is so startling it forces us to rethink, well, everything. But believe it or not, the core idea isn't entirely new. It was actually foreshadowed centuries earlier by the philosopher David Hume. He basically argued that just because something has always happened a certain way in the past gives us no logical reason to be sure it'll happen that way in the future. This really sets the philosophical stage for the mathematical proof that's about to come. The no free lunch theorem takes this almost godlike view of the world. It doesn't look at how an algorithm performs on one specific problem, like identifying cats in photos. No. Instead, it looks at the average performance across every single conceivable problem that could possibly exist. And what it finds is, well, it's truly shocking. When you average their performance across all those possible problems, every single learning algorithm performs identically. I'm not kidding. No algorithm is better than any other. So just how deep does this rabbit hole go? It means that for every single problem out there where a super sophisticated deep learning model beats, say, just random guessing, the theorem proves there is another, different problem where random guessing will beat that exact same deep learning model. When you average it all out, it's a perfect tie. This leads us to a massive, glaring paradox, right? If every algorithm is fundamentally equal when you look at the big picture, then why does machine learning seem to work so incredibly well in the real world? Why are we even talking about this? Exactly. If there's no universally superior algorithm, no free lunch, then what is it that makes one algorithm seem so much better than another for a specific task, like language translation or diagnosing diseases? What's the price we have to pay? The answer is assumptions. You see, an algorithm isn't just good in a vacuum. It seems good because its built-in biases, its core assumptions about how the world works, happen to be a really great match for your specific problem. For example, a linear regression algorithm assumes the relationship in your data is a straight line. If it is, awesome, performance is great. If it's not, performance is terrible. That alignment is the price you pay. Let's break it down like this. The universe of all possible problems is a huge chaotic mess. But your specific real-world problem, it isn't chaotic. It has a particular structure, a certain shape. An algorithm also has a shape. It's built-in assumptions. You only get good performance when the algorithm's shape is a good fit for your problem's shape. You are essentially betting that its worldview matches your slice of reality. And this leads to a really profound conclusion. Choosing an algorithm is not just a technical decision. It's a powerful declaration of your assumptions about the very problem you are trying to solve. And there's simply no way to get around that.
So the implications of the no free lunch theorem are just massive, and they should fundamentally change how we all think about building, choosing, and using AI systems.
The practical takeaways here are truly paradigm shifting. That search for a single, inherently best algorithm, it's over because one doesn't exist. This also means common rules of thumb, like always prefer a simpler model, are just suggestions, not universal laws. And maybe the most important takeaway of all, an algorithm's fantastic performance on one set of benchmark problems gives you zero mathematical guarantee of how it will perform on yours. So at the end of the day, a successful AI project isn't about finding the smartest algorithm out there. It's about finding the best alignment between your tool's built-in assumptions and the specific hidden structure of your particular task. Which leaves us with a final, very provocative question that is more relevant today than ever. As we build and rely on these ever larger, more complex AI models, the no free lunch theorem forces us to ask, what hidden assumptions are we embedding deep inside these systems? And how well are they truly aligned with the world we actually want them to operate in?